Okay, so this is for BUS202, and this is a introduction to some of basically what we mean by descriptive and predictive analytics. Okay, so in this opening chapter, there's a couple things you want to take away from this. Number one is that the idea of our modern world is driven by data, and the volume of data, the velocity of data, makes it imperative that we come up with a means of being able to deal with it and analyze it and cope with it. All right, so the tool we have traditionally had in dealing with data is the field of statistics. All right, so part of what we're covering in this course is statistics, but we're actually doing more than statistics. All right, so we're doing statistics as a foundational component. All right, but we're going to, as we'll see as we go through this, it's not just a stat course. It's an applied statistic with other elements added in. All right. So we're going to talk about a couple things. We're going to talk about a little background about statistics. We're also going to talk about something called the DCOVA framework, right, which is really a structure or a method of performing an analysis that helps us leverage statistics to help solve business problems. All right, and then finally we're going to talk about what is statistics. All right. So the thing is, in the modern world, modern business world, it is really this whole idea of data has become a dominant factor. It's always been there. So when we talk about data, what we're talking about is digital data, right? So as distinct from maybe written data or verbal data. All right. But what's happened is we've basically filled out the digital landscape in terms of technology, in terms of applications, in terms of both applications on the business side, applications on the consumer side, applications on the social side. One of the byproducts is a explosive growth in the amount of data that we are generating, that we are capturing, and that we can potentially process. All right, so this has been a trend that's been going on for some period of time now. So it wasn't, this is not necessarily a new thing. Actually, what we heard was, if you go back, there was a concept dealing more with computing, dealing with what they call Moore's Law. So Moore's Law is an observation by Gordon Moore, who was the head of Intel, that as time goes on, over time, the numbers, the density of microprocessors grows, doubles, which translates to doubling of capacity. So in the shorthand version of that is, computers are getting faster and faster and cheaper and cheaper. So we've seen this, and this cycle has been going on over a 2-year basis. And what's happened is about, starting in like the late 90s, early 2000s, what we saw was an explosion on the data side. So, Moore's Law talks about microprocessors. As we've increased the number of microprocessors, we have at the same time increased the amount of things that are generating data. All right, so it's our universe of digital data is large and getting larger all the time. And one of the challenges from a business perspective is being able to deal with it. It used to be not having enough data. Now it's it's more like trying to figure out and sort through everything you have. You have a torrent, an ocean of data, and then trying to figure out what pieces are the most relevant, what pieces are the most impactful to help facilitate decision making. So this is kind of an underlying concept around our as we're dealing with this. Statistics has been around a while. All right? So the whole idea of statistics really was drawn for the fact that you couldn't test everything. All right. So the idea is if you were manufacturing something and you wanted to get some idea of the characteristics of what you were producing, one way to do it would be to test everything that comes off the line. If you're making millions upon millions upon millions of units, how practical is that? And then also you have scenarios or situations where you end up having to, the testing can be destructive. So what happens is, in order to test something, you have to break it. So if you have a million items and in order to test those million items, you have to break a million items. You might be able to produce it. You might be able to run a test, but you're not going to have anything to sell. All right. So the idea of statistics really came about from the idea of, well, we want to gain insight, the possibility of gaining insights into the characteristics of a set of data or attributes without having to test everything, and being able to come up with something that is statistic or something that's reliable, a reliable form. These are estimations, but they're done in such a fashion. The discipline and the structure we apply to it means that the numbers, we can rely. These are reliable numbers, reliable estimates. All right. So when we talk about business analytics, so statistics have been around. So business analytics is really where we take our traditional statistical stuff and we blend it with areas like management science. So things like sort of a process-oriented approach in organizational structures, combined with modern information systems. All right. So the combination of these three elements together create kind of a new platform that we call business analytics. So it's an interdisciplinary tool, and it really has the objective of supporting fact-based decision making. Right? The job of a manager is to make decisions. Ideally, the manager needs to make as good decisions as possible given circumstances, understanding that you don't necessarily, not all decisions are fully informed. You might not know everything about everything. All right, so you want to make a fact-based decision under conditions of uncertainty, as accurately as you can. All right, and so business analytics is really aimed at being able to provide managers with the tools or a set of tools to be able to do this. All right, so we've always had statistics in business, business school. So it's always been a part of our curriculum. And it remains, an important part of our curriculum. But now its emphasis has changed a bit. We have larger and larger sets of data to work with. Our organizations are finding themselves becoming more and more data-driven. All right, so in order to deal with this, we need to really kind of enhance, and elaborate on our analytical skills. So, and we've seen there's been a lot of work done. This idea of data and big data and analytics has got a lot of press, and there are, not to overstate it, but there are definite advantages, organizational advantages around leveraging, analytics in business decision making. However, you can't have too much of a good thing. So we'll talk about both the pluses and minuses. All right. So this is not absolute guarantee. So this stuff is not absolutely guaranteed to be perfect. All right. But it does give us an informed an approach to be able to make an informed decision. So the structure. So in order to do this, part of the approach we take is actually to use a framework or a structure that will guide us through the series of steps we want to follow in order to make best use of these statistical approaches. So the framework we're using is something we're going to call DECOVA, right? Which stands for, it's an acronym, stands for the process we go through. So the process is, we do a definition of the data. Once we've defined the data, we then look to collect the data from the appropriate sources, organize it, into some sort of structure that makes sense. So usually it could take the form of a table or something of that nature. Once we've done that, we can then go and visualize the data, developing charts to kind of take numerical references and turn that into a visual representation. And then finally, once we've done that, we analyze the data and draw conclusions and present the results. All right. So the COVA is a process. So we'll go through this, step by step over the course of the term. But you want to kind of get familiar with it. But it is the means by which we approach this. It's the algorithm or the process that we undertake when we're doing this. So using the COVA, so really what the framework is there for is to help us apply statistics to business data. The idea is that when we use this framework, we will be able to, we can both summarize and visualize our business data. We can do analysis and reach conclusions about that data. We can make reliable predictions about business activities. Right? And not, note the key word here is reliable, not absolutely correct. Right? So there's still uncertainty, but it's an informed decision. And it also enables us to improve business processes. And we'll talk about that as the shift towards a process-focused business environment where, what we've done is we've created end-to-end business processes that span different segments of the organization, and we've wired them in such a way to be able to capture the metrics of what's occurring and go back and then do analysis against that. So one of the key things we're going to find in this course that we'll have to deal with is the terms. Right? There's a lot of terms within this. So I want to kind of get some stuff down for some of the basic terms, establish them, and then we'll be using these again and again and again over the course of the term. But so the first one we're going to talk about is something we call the variable. Right? So a variable is something we measure. It's a characteristic of a particular item, or individual. There can be multiple characteristics or multiple variables that can be used to describe an individual, such as their height, their weight, their color of eyes, their hair, any number of different characteristics can be used to date of birth and city of birth. So all these things are different variables that describe some aspect of an item or an individual. All right. And then what we do is we have a set of data, the individual values that are associated with a variable. All right. So it could be, say for example, in my case, my height. I have a height. Right, that would be the variable, and 5'7" would be the data associated with the variable that would predict to me. All right. So the idea, and then statistics is really the algorithms and methods that are that have been developed over time to help transfer data into useful information. All right. So numbers by themselves are simply measures. They are signals. They are until we do stuff with them, take data, turn it into information, and then process information to create knowledge. The data is just simply is something that has potential use. All right, and statistics are the means through which we affect that transformation. All right, so there's a couple different ways. There's a couple different branches of statistics. All right. In our course, we're going to talk about two of them. All right. So statistics are, to kind of repeat what we had said, methods to transform data into useful information for decision makers. Right? Within that, they kind of fall into two broad camps. One is what we call descriptive statistics, which is really relates to collecting, summarizing, presenting, and analyzing data. What are the characteristics of the data that we are analyzing? So we're describing something. All right, and then the other one is what we call inferential statistics. So what we do is we draw data. What we do is we draw a sample size, a relatively small sample size, or an adequate sample size, to draw conclusions, analyze that, and then draw conclusions about the large group. All right. We use both. So, statistics, we will be talking about both descriptive statistics as well as inferential statistics over the course of the term. So, formal definition of statistics, as we said, methods that transform data into useful information for decision makers. It is, a very formal definition. It's a set of methods, processes, techniques used for the collection, analysis, and interpretation of data. Right? Has been around, for quite some time. So this has been, going back into like the early days, early corporate environments when we were trying to, when things were probably much more analog in nature. You would create your manual manufacturing processes, and the need to test or understand the characteristics of output. Really was where the foundations of where this came from, and it's been around. So what's happened is we're using the stuff that's out there and has been out there for a while, and really applying it to a modern world, a world that's populated with digital data. So formal description, the objectives, why do we use statistics? What's the objective of it? Is to make it, and describe it as, objective of statistics is to make an inference about unknown populations based on the information contained in a sample. So I can have a set of things. They could be manufactured. It could be a set of individuals. It could be any number of things that would make up a population. We do not know the characteristics of that population, but what we can do using the different methods and techniques of statistics, we can draw a small sample, or a relatively small sample, clearly less than 100% of the sample, and be able to create an inference, analyze that, and then apply the analysis or the results of that analysis to the broader population. So, throwing a couple words there, so we'll kind of back these up. So, a population is all items that of which we want to draw a conclusion. You can call them sets of things. Any collection of items or individuals or whatever that you want to be able to describe and gain insight around. A sample is the portion of that population that gets selected. So ideally, what you want to do is, in order for statistical analysis to work, these samples are random, are meant to be random samples. All right? So you want to make sure it's a representative random sample, because obviously, if you draw stuff and you have bias, if you bake bias into it, that really can distort the outcome of a statistical analysis. Right? So you want to try to be as unbalanced, unbiased as we can. And then finally, inference. And inference is the process of drawing conclusions about the population based upon the information that was gathered and analyzed about, from the sample. So a couple more terms to look, keep on our heads. Random sample, as we just said, is that a formal definition of that is one in which each individual or item has an equal, when they're in the population, has an equal chance of being chosen. right? So if everything has got an equal chance, then and you draw randomly, then it's the outcome of your statistical analysis can be applied to the whole population. A non-random sample is one in which an individual item does not have an equal chance. Now, does everything have to be random? A lot of cases, yeah, it would be better to have it would be better with to have a random sample, but because you just have to kind of understand what makes up the why is something non-random, and then what potential impact it could have on the the application of the inference to the population size, right? So a couple more things. Unit of analysis. Unit of analysis is the whom or what is being studied. Right? So if we're studying voters, all right, so that would make up the population. A population of voters would be the unit of analysis. All right, and then the unit of observation is what we gathered the data from. Is basically what those elements that make up what we are going to be doing our analysis from that population. So, kind of an example of inference is all through 2020 we'd seen a lot of this in dealing with election polls. All right, so so in this case, we had kind of two candidates in the race, Biden and Trump. Our assumption is there are no undecided voters. All right, so that simplifies it, probably to a remarkable degree, because obviously the undecided voters are going to have significant weight on this on this particular analysis. But to simplify it, we're going to say everybody in the population has made up their mind whether they're going to vote for Trump or they're going to vote for Biden. So say a hypothetical result on this when we run. So we drew 1,000, drew a random sample of 1,000 voters, eligible voters. All right, and what we got back was survey results said 520 of those were going to vote for Biden. 480 of those would be voting for Trump, which makes up a population of our sample size of our population is 1,000 voters. All right. So if we translate that into a percentage, assuming 100% combination of the two make up 100%, 52% for Biden, 48% for Trump. All right. So this is our point estimate for this. All right. Now, the question is, though, so you look at this and you say, okay, well, great, I've got this number, but how accurate is this number? What is the degree of accuracy I can attribute to this number? Because just because you took a sample size out does not necessarily mean that it will happen that way. It could, but we're not dealing with exact counts here. All right? So there's what we call the margin of error. All right. So a margin of error is really a level of confidence, a confidence interval, which we want to attribute to that particular analysis. So in this case, we're going to say that the margin of error is going to be plus or minus 3%. Right. So what that means is 3%. Biden, his result would mean that it would be likely it would fall within the range of 49 to 55%, and Trump being at 48%, his range would be 45 to 51. Right. So what that means is it's not just because Biden won the kind of the point analysis from our survey from the sample size of 1,000 there's still a possibility. So he's a lead, but his, as we kind of factor in the margin of error, Trump still has a possibility of winning. So it's not a lock. All right. So this is what we call, with this result, we're saying this is a 95% confidence interval. All right. So it's a relatively low, plus or minus 3%. All right. So in effect, what we would say is the race is too close to call. Now, if we came back with a result, we ran the survey, and we came back with, Biden 12% and Trump 88%, even with a 3% margin of error, it's pretty clear that Trump is a very solid lead. All right. So it's a clear winner in that case, but in most cases, it's really a matter of taking the results of our analysis and applying the level of confidence. What is the confidence interval and the margin of error. Those are the terms that get used around this. So the margin of error is a function of the sample size. So if I draw a larger sample, I can reduce my margin of error. Okay, so say for example, if in this case, if I wanted to have a margin of error of less than 1%, right, plus or minus 1%, I would need to draw like almost 10 times, draw from a sample size of almost 10 times. All right, so maybe 8.5 times the size. So from 1,000 up to 9,000, closer to 10,000. That will give us a confidence level of plus or minus 1%. Right. Whereas if I reduce my sample size, to 384, then my margin of error is actually going to increase from 3 to 5. All right, so there's an understanding when we do this type of analysis that the numbers are not going to be absolute. There are no, this is what it is. It's okay. It's within. We believe this will be within this particular range, and with an associated level of confidence that will be be at that level. So we use the approach we've taken here is we take our polls. Application of estimation is really a statistical inference technique. All right. So, basically a quick summary of what we talked about. Descriptive analytics, probability, inferential statistics. These are the things that we'll be covering in this course, particularly with the idea of doing analyzing sets of data and kind of mining them for the facts that are contained within. All right. And from a just from a high level perspective, this is a picture of kind of the field of statistics. All right. So over on our left-hand side here, we have what we said descriptive statistics. It describes a set of measurements. So we take a set of measurements and it gives us insight into characteristics of something. It can be numerical, it can be graphical, it can be qualitative, it can be quantitative. So it's not the data we bring in, these variables. It's not just always numbers. All right, there are characteristics that we capture as well, in addition to numeric or quantitative attributes. All right, and then along with descriptive statistics, we have probabilities, which is really the approach of analyzing something to be able to identify and quantify the degree of uncertainty. All right, so here's our kind of our basic mechanics around this. Statistical inference, all right, is kind of the other big chunk of what we're going to be looking at over the course of this semester. Is going to be, we're talking about the answers to the unknown populations and parameters. All right, so estimations and testing is going to be really kind of the core, kind of the key in our areas here. All right, so that's everything that we're covering in this course. If you go on and we have other courses, there's actually a course dealing with other types of analytics. All right, more advanced analytics, dealing with regression and correlation, which we talk about what is the relationship between variables. All right, so and this is actually a really big field, in particular, being able to be able to determine predictive, be able to go back and take a look at information and be able to make forward-looking projections. All right. So another thing I want to do just real quickly is show there's a little bit of information here. So there's a slide. We're talking about variables. So I want to talk just a little bit more about variables and the different types. Right? So the variable is really some sort of description of data, and it's data. Right? So a variable is a data element. Right. It can be, the type can be a variable, can either be categorical, which is non-quantitative. All right, high, medium, low would be an example of a categorical, versus numerical, right, which is obviously some type of measurement. All right, and then numerical can be broken down into either discrete numbers, so individual values, unique values, or what we call continuous. All right, which is a time term you'll hear is time series. The arrival of something over a series of events which occur over a period of time. All right, so these are the variables that we're dealing with, and then categorical variable is further broken down into nominal, what we call nominal or ordinal. Right. So nominal, just to give you a little bit of an explanation of this one, all nominal means is we have a named variable. Right? So we have a variable, we give it a name, that makes it nominal. If we give it a name and the sequence or the order of the variable is important, that becomes an ordinal variable. All right, so those are kind of the two examples, on our as we're looking at our definitions of different ways we can construct variables. All right. So these are all kind of the non-quantitative. These are quantitative, so numerical, those are numbers. All right. Intervals and ratios are really the types, the ways we can further structure our numerical variables. All right. In those cases, and the interval is defined as it's a variable that is named, ordered, with a proportionate interval between variables. All right, so you've got some number, basically you have X number of items, of which there is an interval of size n between them. All right, and then finally a ratio A ratio is, it is a named ordered proportionate, and in addition, with a proportionate interval, and can also accommodate absolute zero. So that's kind of what a ratio is. All right. So those are the pieces. So that's basically a starting point for us as we're kind of starting into our discussions of the term, and we'll be building upon this over the next few weeks. Okay, and that is about it. All right. Thank you.